Now we shall discuss some properties of determinants, and we obtained these two. This was coming from the definition. Determinant A is e to the trace log A, and we also, using the definition, obtained determinant AB was determinant A times determinant B, a very important relation. Now we shall obtain various properties of the determinants. For example, let us look at determinant A complex conjugate. So if A is given, determinant A, what is determinant A of the matrix which is complex conjugate? It follows from here, this is e to the trace log A star, and log A star is this A star, etc. So it is e to the trace. You see, you can take this and then star it. So it is log A star. But if you are taking the trace of each term, you can take the trace and then star e to the trace log A star. But exponential is such a series, so you can complex conjugate term by term or sum the series and then complex conjugate. So it is e to the trace log A complex conjugate, but this is simply determinant A. So determinant A star, determinant of A star is determinant A star. So you don't need to take the determinant again. If you found the determinant A, to find to get the determinant of A complex conjugate, you simply take the complex conjugate of the determinant. 2. Determinant of A transpose. Determinant of A transpose. So this is e to the trace log A transpose. So if you look at here, we have, instead of A transpose. So in general, we have this term, trace of A transpose to some power A transpose. So this is the same thing as trace A. So it is equal to the e to the trace log A, which is determinant A. So determinant of the transpose is the same thing as determinant A. This is an easy exercise. If you just take a bunch of A's and if you transpose them, it is A transpose. But we have seen that the transpose, this is a matrix, let's say to the power n. So this is A to the n power, some matrix, transpose. We have seen that when we studied the properties of the trace of the matrix is equal to, and its transpose have the same trace. So they have the same trace. So we can write it like that, which is equal to determinant A. So that's the second. So the transpose of a matrix has the same determinant as the original matrix. All right, so let me erase details. We obtain the results. So let me write it down like this. Now, there is a property that follows from these two, and it is this. In physics, there are some matrices that are self-adjoint or Hermitian conjugate. So, H dagger is defined, I+J is H transpose complex conjugate I+J. It is H.J.I. complex conjugate. So, for example, what is determinant H dagger? This is determinant H transpose complex conjugate. We just proved that this is the complex conjugate of determinant HT complex conjugate, and we just proved again that transpose matrix has the same determinant as the matrix itself, so it's equal to determinant H complex conjugate. So if H is self-adjoint or Hermitian conjugate equal to its Hermitian conjugate, then H dagger is H, so this is equal to determinant H. So if something is equal to its complex conjugate, that means determinant H is real. So Hermitian matrices, which are self-adjoint matrices, self-adjoint means this, their determinants are real. So determinant H is real. All right. 3. What is determinant lambda A? So let's take it from here. This is equal to e to the trace log of lambda A. So let's look at log of lambda A. I will write it like this. I will use this one. Determinant AB is equal to. That means I will write determinant lambda times unit matrix times determinant A. I'm using this property. And this one is e to the trace log lambda I, and let us look what lambda I is. Instead of A, I put lambda I. So log lambda I is equal to lambda minus 1I, lambda minus 1I minus lambda minus here, lambda I, lambda minus 1 square, I square over 2. It goes like this, lambda minus 1 cubed, I cubed over 3, etc. But I is a special matrix, namely I to the n, power n is I. So all these matrices are simply I. So we can collect this lambda minus 1 minus lambda minus 1 square over 2. What's that? That's simply log lambda times I. I is not in the log. This is the log lambda times I. All right. Times determinant A. So I will now take the trace of it. E to the trace lambda I is e to the log lambda times trace I, because that's the only matrix. Trace I is by definition n, if it's n by n. It has ones along the diagonal, and if you sum them, it is n. And this is e to the log lambda n, which is, this is a number, so it is simply lambda to the n. Therefore, we found it, determinant lambda A is lambda to the power n times determinant A. I can erase these. Determinant H is real. 3. Determinant lambda A is equal to lambda to the n times determinant A. So I don't need this anymore. All right. For an important thing that is so easy now to find out, determinant A minus 1 A. This is simply unit matrix, of course, and determinant of unit matrix is 1. But now we apply this determinant AB, determinant A, determinant B. So this is equal to determinant A minus 1, determinant A is equal to 1, and this wonderful result, determinant of the inverse matrix is 1 over the determinant of the matrix. Now let's look at 4, 5. Determinant U A U minus 1. First, you can separate U, determinant U and determinant A U minus 1. Then successively applying this is equal to determinant U, determinant A, determinant U minus 1. But we just proved the determinant of the inverse matrix is the inverse of the determinant. So these things. So it is the same determinant. Just like trace, determinant is invariant under these similarity transformations. If you make, for example, in physics, coordinate transformations, in classical physics or in quantum mechanics, if you use orthogonal matrices or unitary matrices, determinant is invariant. Therefore, determinant A is invariant under similarity transformations. Just like trace. So these are two important numeric invariants of a matrix. Its determinant and its trace. They are invariant under these coordinate transformations. This is a wonderful, physics like to see when you transform things, what thing remains invariant. And here we see that the trace and the determinant remains invariant. And for example, we have to find in the eigenvalue equations, we have to find determinant. For example, A minus lambda I is equal to 0. For an n by n matrix, you have in general n roots. N roots. So that's how we determine the eigenvalues of the matrix A. But we can write it like this: UA U minus 1 minus lambda. Lambda is a number. UI U minus 1, which is determinant U A minus lambda I U minus 1. We set equal to 0. So this determinant is 0 in any coordinate frame. So you pick the coordinate frame where you can solve the problem easiest. You are not stuck with one coordinate frame. You can choose the coordinate frame wherever you want, transformed frame to work with the eigenvalue equation. And this is due to the invariance of the determinant under similarity transformation or coordinate transformations. All right. I can erase this. Sometimes we have to make some approximate computations. For example, suppose we have xA, I, and I is the unit matrix, A is submatrix, and X is a small parameter. X, small parameter. You don't want to solve it to all orders in X. What is the first order in X? So we use this definition. This determinant is e to the trace log I plus xA. I'm using here. And I'm looking here. I plus log of I plus xA. I subtract I from it, so it is e to the trace xA minus x square, a square over 2, etc. It's going. Since I'm going to solve it to first order in X, I ignore x square, so it is e to the trace x times trace a, and you simply expand. This is 1 plus x trace a. So this is determinant I plus xA to order x square. So it's the first order approximation. First order approximation to determinant I plus xA. Now, a very simple generalization of it is determinant A plus xB, where x is again small. But now we can do it very easily. This is determinant A times 1 plus x A minus 1B. So in terms of matrices, A plus x times A minus 1 is unit matrix B. So this is determinant A times determinant I plus x A minus 1B. But we just computed upstairs, so it is determinant A times 1 plus x trace A minus 1B. So this is determinant I plus xA. Approximate, 2 order x square. So I have to erase because I'm out of the book. I'm erasing these. Now, suppose we have the matrix A, and corresponding to it we have the determinant A. Suppose I define a tilde, which is A0, 0, I, where I is n by n, so this is n, m, n, and m. So this is m by m unit matrix IM. Let me call it 0, 1 and 0, 2. 0, 1 is n by m, and 0, 2 is, namely it's an array full of zeros, m by n. So what is determinant A tilde? Now, we put log A tilde. Why? Because we have determinant A tilde is equal to e to the trace log A tilde. And you subtract an I from A tilde, and this is n plus m times n plus m dimensions. So if you subtract it out, in a typical term, you will have this A tilde minus I will be A minus I in the n by n part, 0, 0, and the lower part will cancel. So you will have 0. So you will have powers of it. Let's take the second power, A minus I square. You see, you can easily multiply because they match. So it is, this is A minus I square. And everything else will be 0, 0. So when you are taking the trace of it, you will be taking the trace of the powers of A minus I. Here I is the n by n. So trace will be this trace of log A tilde is the same thing as trace of log A. So it is e to the trace log A, which is simply determinant A. So what's the result? Let me just say it again. If you have a matrix A0, 0, I, this is n by n, this is m by m. So the determinant of it is equal to determinant A. Also, you can put I here, A here, it will be the same. Let me erase the calculation, let the result remain. Also, it is trivial, it follows the same line. I, 0, 0, A, that's also determinant A. Now, how about determinant of A, B, 0, C? These are block matrices. What are we doing? We are studying the determinants of block matrices. So we will try to write these block matrices as much as we can in terms of such matrices. So for example, we can use A0 I, let's say B, times I0, 0, C. Let's check, does it give A, B, 0, C? First one, this is the n by n block, this is the m by m block, and these are nm and mn. So this is A, all right. This is 0. This is B, all right. And this is C. So it checks. Now, the determinant of it is C. We just proved. Now we have to check this one. New A tilde. So this is new A tilde. So the determinant of A tilde, so if you write it, it's the determinant of that and determinant of this. The determinant of it is determinant of C. Now what happens here, determinant A tilde, this will have e to the trace log A tilde, and A tilde is a series expansion of this form, and you subtract an I. When you subtract an I, you have powers of this matrix. A minus I, 0, B, I minus I is 0. So let's look at, for example, the second power, A minus I, 0. This doesn't contribute, here B does not contribute to the trace. Let's check in the second power, 0, 0, that's equal to, this is A minus I square. This is 0. This is B times A minus I and 0. So if you multiply with the cube, B always will remain here, will never come to a position to contribute to the trace. So the B will not contribute to the trace. That means it will be like this one, and it is simply the determinant of A. So it is simply determinant of A0 BI determinant of I0, 0, C, which is equal to, this is determinant A, and this is determinant C. So B doesn't play a role in the determinant, in the block matrices. So let me write it here. Determinant A0, B, C is equal to determinant A times the determinant C. It is clear that A, B, C, 0 with a different B, let's say D. This will be again determinant A, determinant C. Whether we have a block matrix here or block matrix there doesn't matter. I am erasing. Now, in a more general case, determinant A, B, C, D. Again, we have to write it as this thing as multiplication of two matrices A, B, C, D, and let's try A0, C, IM. We simply try something that will IN. Now, of course, the rest we don't know. X, Y, let's say Z. And let's find X, Y, Z. That's equal to, this is A, and this is AX. This is C plus Y. This is CX plus Z. This will be equal to A, B, C, D. So let's find this. AX is equal to B. If I multiply from the left by A minus 1, X is equal to A minus 1B. Okay. This is C plus Y. C plus Y is equal to C. That means Y is equal to 0. And Cx plus Z. C is A minus 1BZ. So A C, X is A minus 1B, X minus 1B plus Z equals D. Therefore, Z is equal to D minus C A minus 1B. So, this is determinant of A0CIM, determinant IM A minus 1B Y is 0 and Z is D minus CA minus 1B. But these determinants are now trivial because this is simply determinant A and this is simply determinant of that. So where shall I write? Determinant A, B, C, D. That's equal to determinant A times determinant Z, which is D minus C A minus 1 B. You can also decompose it, I will not do it, but you can decompose it such that you have the x, y, z here, and you write simple matrix here, you multiply, and then you will have it in the form of determinant D, etc. But I leave that to you as an exercise. So I'm also, because of time, I'm not do it. And you got the flavor of it. Now there's another important matrix. We played with the trace. What if A is I minus lambda AB? We are looking for the determinant A. So A minus I is minus lambda AB. And we put it in here. Okay, determinant A is e to the trace log A. And in the log A, we have A minus I. So this, we have e to the trace of, minus lambda AB. That's first part. Then the square of it, coming with a minus sign, minus lambda square over 2, A, B, A, B, because we are taking the square. And when you take the trace, let us remember, trace AB is simply BA. Is this complex number. So we have e to the, we take the trace, minus lambda BA, minus lambda square over 2, BA square, minus lambda cubed over 3, BA cubed. There is no matrix left after taking the trace, and this is simply e to the log of 1 minus lambda BA. Because here you can use with the scalar 1 minus 1, so it's minus lambda BA, minus that, minus that. Therefore, this is just a number. E to the log is this thing, 1 minus lambda BA. So the determinant of I minus lambda AB is equal to 1 minus lambda BA. All right. So the determinant of this A is 1 minus lambda BA. I'm erasing all this. Now, one last thing and we will finish this. We said that by the definition of determinant, log determinant A was delta trace log A, and this was trace of 1 over A delta A. Let's look at here. This is a number, therefore this is delta determinant A divided by determinant A is equal to trace, let me take it to here, delta A 1 over A, or delta, if you vary the determinant A, this is equal to determinant A trace delta A 1 over A. All right. So, for example, if you take a variation with respect to x, if A is a function of x, this is delta x, determinant A is determinant A times trace of delta A delta x, whatever that derivative is, times 1 over A, and you take the trace. Let's take a particular x, because it's interesting. Let's take the derivative of determinant with respect to an element of the matrix. So let's take x equals aij, one particular element. So delta determinant A delta aij is equal to determinant A, and then under the trace delta A delta aij times A minus 1. So delta, here in the matrix product we have delta, for example, pk and A minus 1 k p, and there's a sum over k and there is a sum over p. So sum over p and k. K sum is the matrix product of delta A with A minus 1, and P is for the trace. We are summing over the diagonal elements. And now we are taking the derivative with respect to delta aij. Well, if you take all elements to be independent, there is only one term that contributes. We have here delta IP delta JK. That's the only thing, because all other elements are independent. Then we have A minus 1 KP, sum over P and K. That's equal to P will be equal to I, so I have A minus 1 I, and K will be equal to J. So this is the only thing that survives. A minus 1 Ji, or the Ji element of I. So if I write it out, delta determinant A, delta Aij is equal to determinant A times Ij Ji. Okay. So we obtained many properties of determinants using this definition, and so looking at A as a total one matrix, we obtain its determinants. There are other properties of determinants because it's the determinant of a matrix. So for example, what happens if you change the rows, if you change the columns, if you add them, etc., then you need another representation of a determinant, which, however, we will not do it here. But we obtained many important and sometimes difficult to obtain properties of the determinants using that definition. Thank you.